Hello, everyone. Let's continue with the ordinary differential equations we had. The other day, we mostly talked about homogeneous linear ODEs, right? Today, we want to focus on non-homogeneous ones. So I just want to say a few things before starting to before going to our examples. One is that I would strongly encourage you to look at the notes. I've uploaded the notes on the course page, the web page of the course. So the point is that these equations usually get so complicated very fast. So if you don't probably review every day the things we discussed in the class, very soon you will find it very hard to follow. Especially that we have a very short semester, right? So there's not much time. So probably it's best if you review every course the next day. You can look at my notes or you can look at the book. Okay. Okay, let's continue. So let's continue with non-homogeneous linear ODEs. So the topic today is non-homogeneous linear ordinary differential equations, right? So what's the difference? So for example, we looked at some first order linear differential equations, something like this. Dy dx plus fx times y equals 0. Now, non-homogeneous means there is another term plus gx here. We have some extra non-zero term which does not have y. It's not a function of y. This is a first order example. A second order example would be something similar. So let's say the second derivative of y with respect to x plus some fx dy dx plus some function gx times y. Well, the homogeneous would be this thing equals 0. The non-homogeneous would be this one. There is another function h of x here. And this h of x is non-zero. So the problem is that how can we solve this one, right? The simplest example, let's look at a very simple example which we can solve without any specific knowledge of any technique. So for example, dy dx, suppose, is equal to just f of x. Well, this is non-homogeneous, but it's very simple to solve. Suppose we want to solve this one. So what are we going to do? Well, we are going to just separate the variables. That would be our first step, like the previous examples we saw. And then we are going to integrate, right? Because we want to find what is y. And then, as you remember, the integral and the differential, they kind of cancel each other up to a constant. So the result would be integral of fx dx plus some constant c. So that's a very, very, very simple. That is, here we can see a very simple non-homogeneous linear ODE. Okay, let's now look at a more complicated example. How can we solve it in general? Let's look at another example. So let's suppose we have this ODE. The second derivative of y with respect to x minus 2 times derivative of y with respect to x plus y, let's say, is equal to 1. 1 is probably, well, it is the simplest term we can have, which is non-zero. So solve this one, right? Think about this one for maybe 2 minutes and then just try everything you can. Let's see if we can solve it or not, okay? Okay, does anyone have any suggestion? I can see one answer proposed here. Let's see if that's the answer. So yeah, I think that is correct. Yes. I think the answer by Anthony, I think that is correct. Let's see. So the idea here is, that's always, I think, the idea is first to consider the homogeneous equation. So first, consider the homogeneous equation. What do I mean by that? Just ignore that term which does not have y. So it would be the second derivative of y with respect to x minus 2y derivative of y with respect to x plus y equals 0. Right. Now, we know what kind of ODE this one is. This is a second order linear ODE with, well, the important property of this ODE is that the coefficients are all constants, right? The coefficient of d squared y over dx squared is 1. The coefficient of derivative of y with respect to x is -2, and the coefficient of y is just 1. Right here, we only have constant numbers, right? So it is an ODE with constant coefficients. Now, when we have an ODE with constant coefficients, we should look at the characteristic polynomial. Now, the characteristic polynomial here would be k squared minus 2k plus 1. We should let that be equal to 0, and we should solve this polynomial. Now, this polynomial is equal to k minus 1 squared equal to 0. Therefore, k is equal to 1. This polynomial has just one solution. Now, remember, when we have just one solution, the two solutions we get for this homogeneous equation, one of them is e to the kx, which here is just e to the x. And the other one is x times e to the kx, which is this one. So the general solution would be just, so let me use UH for the general solution to the homogeneous polynomial is just going to be C1 e to the x plus C2x e to the x. Now, this is the solution to the homogeneous part. It is not a solution to the non-homogeneous equation. So the idea is that the general solution to this equation, the real solution we are looking for, has two parts. One part is exactly what we found. One part is the solution, the general solution to the homogeneous equation, which is exactly what we found here. But the solution has another part. What is that other part? Let me show that with YP. That is one so-called particular solution. Yes, that is correct, John. One particular solution to the non-homogeneous equation. What do I mean by that? Let's look at the equation we have again. This was the original equation we started with. I'm not looking, at this point, I'm not looking for the general solution. Just tell me one solution to this equation. Even if the solution very trivial, it doesn't matter. Just give me one function, y of x, let's show it with yp of x equals to something such that it satisfies this equation. There is a very trivial one which we can just guess. Yes, that is correct, Thomas. That's just one, right? Suppose y is equal to 1, just a constant function 1. The second derivative of the constant function 1 is 0. The derivative of the constant function 1 is again 0, plus 1 y, which is just 1, and the result would be 1, right? So this function is a very, very specific function, just one solution of this equation. Now, the general solution to this non-homogeneous equation would be the general solution we found for the homogeneous part in the previous page, plus this very specific solution we just found now, which is 1, right? So the general solution to the equation would be what we found before, c times e to the x plus c to x e to the x. The solution to the homogeneous part. So solution to the homogeneous part, plus what we call a particular solution, just one solution to the non-homogeneous part. Okay, there's some would give you the general solution to the equation, to the non-homogeneous equation. Okay. Now let's make it slightly more complicated. Sometimes this non-homogeneous part itself can have different terms. So for example, let's consider this other equation. Suppose the second derivative of y with respect to x minus 3 dy dx plus 2y. Now it's not just equal to 1, but it's equal to 1 plus something else, say 3e to the 2x. Now let's try to solve this one. Okay, think about this one again for 2 or 3 minutes, and then I would solve it. Okay, does anyone have the answer? Okay, well, we have one answer. Which I'm might be correct. Let's see. Okay, let's see. So let's start again with the homogeneous part. So we would have the second derivative of y with respect to x minus 3 times derivative of y with respect to x plus 2y is equal to 0. I think I would prefer to make the question slightly different. I would tell you why I'm doing that, and I would come back to solve this problem. So maybe rather than having 3 times e to the 2x, it would be great if we have, say, e to the 3x. Let's change the question slightly. We would come back to this question, okay? Because it makes the question slightly easier. So that would be great if we first solve the easier question, and then we would go to the harder one. So let's consider first the homogeneous equation. It's second order linear ODE with constant coefficients. The characteristic polynomial would be k squared minus 3k plus 2 equals 0. The solutions to this equation are, what are there? Well, k minus 1 times k minus 2 equal 0. Right, so k is equal to 1 or k is equal to 2. So the general solution for the homogeneous part is a linear combination of e to the 1x and e to the 2x. So it would be c1 e to the x plus c2 e to the 2x. Now we should consider the non-homogeneous part. So the idea is that we should break it into different parts. So the idea is that first consider, say, this part, and then we would consider this other part. Okay, so first we consider the non-homogeneous equation, but we would only consider one. So we would only consider equals 1. And we would look for a particular solution for this equation. So again, similar to the previous problem, this equation has a very simple solution. Yes, that is correct. It is just 1/2, right? Because it's constant, so its derivative and second derivative would be 0. 2 times 1/2 is equal to 1. That is correct. Now, in the second step, we would look at the same thing, but now we wouldn't consider this part. Instead of 1 as the non-homogeneous part, we would consider 3 times e to the 3x, right? So we would consider this equation. So now we consider d squared y over dx squared minus 3 dy dx plus 2y is equal to 3e to the 3x. Now we are looking for a solution to this equation. So I'm looking for a very, very particular solution. Let's call that with yp2 of x to this equation. So what is the particular solution to this one? I want to guess what is the solution to this equation. So how can I guess? The idea is that, you see, look at the right-hand side. On the right-hand side, we have e to the 3x, right? Yeah, I think John's answer, I guess it is correct. So the idea is that if y itself is a number, constant number, times e to the 3x, for some suitable a, we can hope it would solve this equation. Because when you have something like this, its derivatives are also, they also have the same form, right? Because when y is some constant a times e to the 3x, the derivative of y also has this form of a constant times e to the 3x. The second derivative also has this form, a constant times e to the 3x. So we can hope a linear combination of them, well, of course, a linear combination of them would also be equal to a constant times e to the 3x. So we only need to find this constant a. And I'm going to plug in these results into this equation. So the second derivative is 9a e to the 3x minus 3, its derivative, minus 3a e to the 3x, plus 2y, which is 2a e to the 3x equals 3e to the 3x. As you can see here, we have 9a e to the 3x minus 9a e to the 3x. So these two cancel each other. Therefore, we get 2a, and also here e to the 3x cancels e to the 3x, right? Because it is non-zero, we can divide everything by e to the 3x. So 2a is equal to 3. Therefore, a is equal to 3/2. Now that gives us our answer. So here we assumed y is equal to a times e to the 3x. Now that shows us this particular solution is equal to 3/2 e to the 3x. Now the final answer, the general solution to the equation, is just combination of these things. So we had, so our general solution has now three different parts, right? One is the solution to the homogeneous part. One is first particular solution we found for the term 1, and then plus the second particular solution we found for 3e to the 3x. All right, so the first part was equal to, I think, c1e to the x plus c2e to the 2x. The first particular solution was 1 over 2, and the second particular solution was 3 over 2, 3e to the 3x. So this sum is the general solution to our equation. So if there are more terms, we just do the same thing. We would break it into different equations, and we should find the particular solution to each one separately. So as you can see, finding this particular solution might be a little bit tricky. So how to find the particular solution? It seems we can, most of the time, it seems we can guess, but it's good to go over to make sure if we know how we are going to do that. So let's consider different cases. Suppose we have some equation which has some number of derivatives of y with respect to x. In general, it might be order n. And then there are a lot of, say, functions fn minus 1. This is just some function, n minus 1 derivative of y with respect to x, etc. So if this thing was equal to 0, it would have been homogeneous, but if it's equal to something else, it's not homogeneous. So what are the possible things we can put here? Well, we can put anything here, but in some cases, for some choices of, let's show this one with g of x. For some choices of g of x, we kind of know what is the particular solution. So in the previous examples, in one case, g of x was equal to 1. In the other case, g of x was equal to a number times e to the 3x, right? I think 3 times e to the 3x. So what are the other options for g of x which it's easy to find the solution? So if g of x is equal to a constant c, it's easy to guess what is the particular solution. The particular solution would also be a constant. So the particular solution is another constant, let's say c1. If this function g of x is of the form we just saw, a e to the ax, just like we guessed earlier, the particular solution would be another constant e to the b times e to the ax. So the only point is finding this b, and just the way we did, you can plug that inside the equation, and then we would find what is this constant b. For example, if this function g of x is a linear combination of trigonometric functions, something like this, say a cosine of some ax plus b sine of some ax, the particular solution also has the same form. The particular solution is of the form some constant cosine of ax plus another constant sine of ax. And that's because we know the derivative and second derivative and third derivative of these functions, they have the same form, right? If we have sine of x, its derivative would be cosine of x. Its derivative would be minus sine of x, etc. So we can expect, if we choose y to be the trigonometric functions, the linear combination of their derivatives, or even with some, actually, I think I made a small mistake here. I should just say it. I'm assuming these things are constant. Sorry, not any function. This is, let's use some constant. Let's say C n minus 1. Actually, that's an important thing. C1 and C naught. Okay, and here rather than C prime, let's use another thing, another constant, D. So if we have the equation is equal to sine plus cosine, those things, we can be sure that a particular solution would be a linear combination of things of the same form, sine, cosine, at least in most of the cases. There's some few counterexamples which we will talk about. If the g of x, the non-homogeneous part is a polynomial in terms of x, say it's a n x to the n plus, say, a1 x plus a naught, the particular solution corresponding to this thing, again, is a polynomial which its degree is less or equal to this one. So it's something of the form bn x to the n plus b1 x plus b naught. We don't need to look at any higher order terms. We can also have a kind of combination of these things. For example, gx might be, let's say, a multiplication of a polynomial, something of this form, and an exponential function. Again, the particular solution to that, for that, is something similar. The particular solution would be a polynomial in terms of x, but at most degree n. This n is not the same n as we had in the equation. Maybe it's better to choose m rather than n. It is some degree, some natural number, e to the ax. That would be the particular solution. And the same thing is also correct for sine times polynomial, cosine times polynomial, etc. Let's look at one specific example to make sure we understand this thing correctly. Let's look at this example. Let's say the second derivative of y with respect to x minus 9y is equal to, well, here let's take gx, this function we're talking about. Let's take it to be x times e to the x. Here we have multiplication of one polynomial and the exponential function. Okay, think about this one for a few minutes and then I will solve it. Okay, let's see. So again, we would start with the homogeneous one. The homogeneous equation is d squared y dx squared minus 9y equals 0. And the characteristic polynomial would be k squared minus 9 equals 0. Okay, it seems we have an answer. Yeah, that might be correct. That looks correct. Let's see. So we have the characteristic polynomial. We would solve it. These solutions are plus and minus 3. So our solution has two parts. One part is related to this homogeneous equation, and the solutions are linear combination of e to the 3x plus e to the minus 3x. Now we need to find a particular solution, right? Looking for a particular solution. Here gx is equal to x times e to the x. Now here, this polynomial we have here has degree equal to 1. Now we talked about this. If gx is equal to a polynomial times e to the x, our particular solution also has a polynomial times e to the x. And this polynomial also has degree equal to 1. But just be careful, polynomial with degree equal to 1 is not necessarily ax. It's a1x plus a naught, right? It might also have a constant term. We should be careful about that. Okay, so our particular solution is something like a1x plus a naught times e to the x, which is a1x e to the x plus a naught e to the x. Now the idea is that to plug in this solution into the equation. So what was the original equation? Let me write that again here. 9y equals x e to the x. We want to plug in this y into this equation to find a1 and a naught, right? So if y is equal to that, yp prime, its derivative is equal to a1 e to the x plus a1x e to the x plus a naught e to the x. Its second derivative would be equal to a1 e to the x plus, again, a1 e to the x plus a1x e to the x plus a naught e to the x. So the first one is equal to a naught plus a1 e to the x plus a1x e to the x. And the second solution is equal to 2a1 plus a naught e to the x plus a1x e to the x. And the y itself also is equal to, well, we have it here. A1x e to the x plus a naught e to the x. Therefore, the second derivative minus 9 times the function itself is equal to this. Right? Now let's simplify it a little. So here we have 2a1 minus 8a naught e to the x minus 8a1x e to the x. Right? And we want this to be equal to, this is what we want. We want this to be equal to the right-hand side of the equation, which is x e to the x. Now, on the right-hand side here, the coefficient of e to the x is 0. Therefore, this term should be equal to 0. Should be 0. On the right-hand side, the coefficient of x e to the x is 1. Therefore, what we have here should be equal to 1, right? So it gives us two equations. I would just write them right here. One of them is minus 8a1 is equal to 1, which that shows us a1 is minus 1 over 8. That's one of our variables. The other one is 2a1 minus 8a naught should be equal to 0. But we know a1 is equal to minus 1 over 8, so 2 times that is minus 1 over 4 should be equal to 8a naught. Therefore, a naught is minus 1 over 32. So that's the other one. If we plug these numbers into our particular solution, we see it is equal to minus 1 over 8x e to the x minus 1 over 32 e to the x. So yeah, so I think Austin's solution was correct. So this is our particular solution. Now our general solution would be this one plus what we had before. So we had this thing here. This one was our solution to the homogeneous part. We should add this one to the solution we got to in the other page. So our final solution is this thing C1 e to the 3x plus C2 times e to the minus 3x plus, okay, plus what we had there, plus minus 1 over 8x e to the x minus 1 over 32 e to the x. Okay. Now, things also can get slightly more complicated. There is a kind of a bad news. So what is that? If you remember, the first problem, I kind of modified the first equation slightly from e to the 2x to e to the 3x. So that's related to this thing. So if you're solving one of these non-homogeneous differential equations, so you first find some solution to the homogeneous part, right? And later you go to find some solution for the particular solution for the non-homogeneous part. Now, if the particular solution has a term in it, which is, that term is also a solution to the homogeneous part, the argument I just told you doesn't work. It might look a little confusing at first, but I would explain that. So what do I mean by that? For example, let me give you an example. Suppose, consider this equation. The very first equation I wrote actually has this property. Consider this equation. So if I want to solve this equation, I should first look at the homogeneous part, which is this one. And then I should solve that. Well, I should look at the characteristic polynomial is k squared minus 1 equals 0. Therefore, k is equal to plus minus 1. And therefore, the solution to the homogeneous part is c1 e to the x, c2 e to the minus x. That's great. Now, I want to find the particular solution, right? The second step is to find the particular solution. So how should I do that? Now I'm looking for a particular solution. This is of the form a polynomial times e to the minus x, right? So the solution should be some first order polynomial times e to the minus x. First order means a1x plus a naught, right? But the point is that here we have e to the minus x. And we also here had e to the minus x. And if this thing here, if the final solution we find has a term like e to the minus x, which does satisfy the homogeneous part of the equation, if you follow the idea we had, it breaks down. So I really want you to try to solve this equation exactly the way we did the previous one to see what happens, to see why it doesn't work. And then I would tell you how we can modify our technique so we can solve this one. So solve this equation. The second derivative of y with respect to x minus y is equal to x e to the minus x. Think about this one for a few minutes. Okay, let me try to do it the wrong way, right? To see why it doesn't work. So as I mentioned, we would look at the homogeneous part of the equation, and then the solution would be C1 e to the minus x plus C2 e to the x, right? And then I should find a solution, a particular solution, so yp of x, and it should be a first order polynomial, a1 x plus a naught e to the minus x. And we note that this term e to the minus x also appears in the solution for the homogeneous part. And this will cause us a problem. So how can I find so what am I doing? I'm looking for a naught and a1. I want to see what are these coefficients, right? So how can I find them? I should just plug in yp into the equation. So derivative of yp is equal to, maybe I should just multiply them first. I should just say this part is not a part of the homogeneous solution. Only this part is, because we have something times e to the minus x. We do not have anything times x e to the minus x. So this part is good, this part is bad. But anyway, so let's take derivative. We would get a1 e to the minus x minus a1 x e to the minus x plus, minus a naught e to the minus x. That would be the derivative of this thing. And now we should take the second derivative. So the second derivative would be, okay, it would be minus a1 e to the minus x minus a1 e to the minus x plus a1 x e to the minus x plus a naught e to the minus x. So that's the second derivative. Now we should just plug them into this equation to see what we would get. Okay, so what we would get is, so the second derivative minus y is equal to minus a1 e to the minus x minus a1 e to the minus x plus a1 x e to the minus x plus a naught e to the minus x minus a1 x e to the minus x minus a naught e to the minus x. And we want this to be equal to the non-homogeneous part of the equation, which was x e to the minus x. Now, well, let's look at the left-hand side. Minus a1 e to the minus x, this one, and then we have, what else we have? Oh, we have the same thing again here. So we would have minus 2a1 e to the minus x. That's great. What else? We have a1 x e to the minus x. We have negative of that. They would cancel each other. We have a1 e to the minus x minus a naught e to the minus x minus a naught e to the minus x. And we want this to be equal to x e to the minus x. Well, we can cancel e to the minus x from both sides. It means a1 is equal to x over minus 2. Remember, we were looking for constants, a1 and a naught. a1, the solution we got here, is not a constant. And that's not good. That's not what we were looking for. We were looking for constant terms to get our solution. So there are different ways to go around this problem. I think it's time for a break. I guess I passed the break time by 2 minutes. So let's have a 5-minute break. Let's come back at 7:25. and then I would tell you how we can solve it. Okay, so one answer is that, well, it doesn't matter if it's not constant. Why do we need it to be constant? We found some A1. Isn't that enough? We found some A1 and we can just write A1 to be x over minus 2. So let's go back. We were saying our solution should be this, this thing here plus some particular solution, which is A1x. And now we're saying A1 is just x over minus 2 times x, x e to the minus x. Right? Plus some a naught e to the minus x. Well, we would have x squared here. And we can say that's the solution. What is wrong with that? There is no reason for these things to be there. There was no reason for them to be constant. We can just say this sum is the solution. So one small thing you might note is that the equation we had did not give us what is a naught, right? Look here. We were supposed to solve this equation to find a1 and a naught, but actually everything which contains a naught, they kind of cancel out. This term has a naught, this term has a naught, they cancel each other. At the end, we don't get anything with a naught in it. So we don't get anything with a naught, but that makes sense, you know? That is what really makes sense. Because here we have something times e to the minus x, and its coefficient can be anything. So it doesn't matter what is this a naught. We can add these two things, and their sum would be another constant e to the minus x. So I can just absorb this term into the other one, and I can just erase this one. That would be the final solution. So that's one way to do it. So just continuing and not looking for necessarily constant coefficient, but any kind of coefficient we would get, and then call that an answer. Another way which you might see, especially in undergrad books, because they don't want to make things complicated. So the idea is that if you solve the homogeneous part, and the solution is something like e to the c times e to the x plus c2 times e to the minus x, and you look at the particular solution, and the particular solution is something like this. What they say is that if the particular solution should be something like this, just multiply everything by x. So if I do that, I would get something of this sort. And as you can see, neither of these two terms really appear here. So everything's good. Take that to be the particular solution and then plug that into the equation. So that would be the technique. But it really doesn't matter. We can just follow the previous algorithm, and a naught or a1, they wouldn't be constant, and it's still okay. It's fine. Okay. So that's how we solve the previous one. Okay, so I think one person mentioned Anthony, I think, mentioned variation of parameters. That is correct. So the point is that usually this word is used when these things here, a naught and a1, are not constant. So they can be anything, any function. Let's write another example. Suppose suppose we have this equation. Solve this equation. dy dx is equal to y plus x to the 5. Think about this one for a few minutes, and then I would solve it. Okay, so again, the first step would be the homogeneous, thinking about the homogeneous equation, which is just dy dx equals y. Well, this one is very simple. This is a separable equation. Dy over y is equal to dx. We separate the variables, and then we integrate both sides. The left side would be the ln of absolute value of y. The right side would be x plus a constant c, and therefore y would be a constant times e to the x. That would be the solution to the homogeneous part, right? Now we want to find a solution for the non-homogeneous part. So the idea is that maybe it is correct that if we plug in this y into the equation, dy dx would be equal to y, right? If we plug in this one, it is a solution to the homogeneous part, so that's what we would get. Therefore, dy dx minus y is equal to 0. We want it to be x to the 5. Well, actually, his solution might be correct, actually. Maybe I made a mistake. So we want, but what do we want? We want this thing to be x to the 5. That's what we want. So sometimes the idea is that maybe if we define another function zx to be something, well, let me show it still with y. Yeah, let me show it with z to the cx. Maybe if we get this function y we had and multiply it with another function, say u of x, which here now it's c e to the x times u of x, or we can absorb this constant c into u. Maybe if we multiply our solution by another function, the whole thing would be a solution to the equation, right? That is the idea. That's what usually called variation of parameters. So let me write it. Variation of parameters. So what does it mean? It means you have an ODE like here, which is not homogeneous. It's non-homogeneous. You consider the corresponding homogeneous ODE. You find one solution for that. Now you hope that there would be another function. So let's show the homogeneous part with YH. You hope there would be another function U such that if you multiply them, you would get a solution for the non-homogeneous equation. So if that's supposed to be true, we should be able to, let's show this one with general solution. We should be able to plug in this multiplication into the equation and it should be an answer. So derivative of this thing we have here, yh of x ux with respect to x minus yh of x ux. We hope it would be equal to, sorry, it wasn't x squared, it was x to the 5, right? We hope this would be equal to the x to the 5. Okay. So what is the derivative? Well, the derivative is just derivative of UH, the x times U plus U time derivative of U with respect to x times YH minus YH U equals to x to the 5. Now we know what is YH here. Our solution to the homogeneous part is just e to the x. Remember, there was a constant c, but I can absorb that into u. So I can just take UH to e to the x. So its derivative with respect to x is e to the x. E to the x u plus derivative of u with respect to x times e to the x minus e to the xu equals x to the 5. Here, YH is e to the x. So, well, that's the beautiful moment in mathematics. These two cancel each other. And we would end up with du dx, e to the x equals x to the 5. Now I understand why you say it's long. That's because of the number 5. So now we need to find, what are we doing? We want to find u. So we separate that. So du is equal to x to the 5 divided by e to the x times dx. We have separation of our variables, and then we can integrate. The left-hand side would be ux. The integral cancels the differential. The right-hand side would be this integral. Yeah, and this is going to be a long integral. I'm not going to do that. You're definitely right. So the way to do these integrals are integration by parts, but it needs more than one integration by parts. I guess we should do 5 in 5 steps. We should do integration by parts 5 times. We are not going to see something like that in the exam. It's going to be very long. But whatever it is, with integration by part, we can solve it. And then the answer, the final answer to the equation, general answer would be ux, which is this thing here, times the solution we had before, times the solution to the homogeneous part. Yeah. Okay. Any question here?
Yeah, so I thought earlier you had mentioned that if you have a polynomial as your g of x, that the solution will also be a polynomial. Is that not true?
That is true. That was you see, that was a different path which we could take here. I can solve this one with that technique. I can solve this one with this technique. At the end, we would end up with the same results. Yeah.
Okay.
Yeah, I mean, here we did not really, so probably that well, I'm not sure which one would be easier here, but here, if we do the integration by parts and, go into it and do it the other way.
Or you have an equation with 5 variables. Yeah.
Yeah, exactly. So if I do that, I would have a lot of variables. Yeah, that is true. I would have a degree 5 polynomial, and I should put that into the equation, things like that. So we can do well, a lot of times there are different ways to solve a differential equation, and any way that works is fine. We are just reviewing different ways because sometimes some of them work and some of them doesn't work. Yeah, so let's consider another example. This is one bad thing about Zoom. There is a maximum number of pages. There are 12. When after 12 pages, I should erase the previous pages again and start from the beginning. Okay. So let's do another one. Solve this one. D squared y dx squared minus 4 dy dx plus 4y minus x squared equals 0. Solve this one. Okay, then. So let me write down the solution. Let's see. So again, we would look at the homogeneous part. Let's see. So the homogeneous part would be the second derivative of y with respect to x minus 4, derivative of y, derivative of x plus 4y equals 0. And okay, we have a solution from Anthony. That looks correct. Yeah, let's see if I can get the same solution or not. And then we would look at the characteristic polynomial. Sorry, k squared minus 4k plus 4 equals 0, which means k minus 2 squared is equal to 0. Therefore, both solutions are equal to 2. At this point, we know that this homogeneous solution is a linear combination of e to the 2x and x e to the 2x. So C1 this one plus C2 the other one. Now we should look at the we should look at the non-homogeneous part. So I want to do it using this recent technique we had, this variational technique we had here. So there is a point here. I have two coefficients. The point is that I cannot absorb both of these coefficients into the other part of the solution. So I'm looking for the general solution. I'm assuming the general solution is this solution to the homogeneous part times another part. I really don't know if this technique works here or not. I just want to try. So sometimes you just need to try. And I really don't know if this works here or not, right? So I would take C1 to be equal to 1. I can absorb one of these coefficients into the other part u, but I can't do anything about C2. So I will keep C2 as a constant. So the solution would be some ux times e to the 2x plus cx e to the 2x. It should be something like this one. This is supposed to be the final solution. So let's take derivative. Its derivative would be u prime of x times e to the 2x plus cx e to the 2x plus u of x times 2e to the 2x plus ce to the 2x plus 2cx e to the 2x. Actually, I can combine the first two terms. It would be 2 plus c e to the 2x. Now let's go to the second derivative. It would be the second derivative of u e to the 2x plus cx e to the 2x plus derivative of u times 2 e to the 2x plus c e to the 2x, which, as we saw before, it's 2 plus c times e to the 2x plus 2c x e to the 2x. Okay, great. Plus, you should also pay close attention because there's a great chance I would make mistake. So it would be great if you also follow closely. Plus u prime of x times exactly the same thing we had before. 2 plus c e to the 2x plus 2cx e to the 2x. Plus ux times the derivative of what we have in the parentheses. It is equals to 4 plus 2c e to the 2x plus 2c e to the 2x plus 4cx e to the 2x. I can actually combine these two I would get 4 plus 4c. And I would just get rid of this one. Okay. Now also note that what we have here is u prime times 2 plus c times e to the 2x plus 2cx e to the 2x is exactly the same thing as we have here. So I would just multiply this one by 2 and I would erase the other one. So plus this thing. So that is the second derivative. Now, what we want to look at is, okay, this is a little complicated. So what we want to do is we want to plug in these things into the equation. So the equation was, I would just write down the equation here. And we hope this thing is equal to x squared. Okay, I would just plug in these things into this equation. Let's see if we can do it. So the second derivative is equal to second derivative u double prime e to the 2x plus cx e to the 2x. I can see my previous page here, so I'm just copying this part from the previous page. So I'm just writing down what we had for the second derivative. And we had 4 plus 4c e to the 2x plus 4cx e to the 2x. Okay. Minus 4 times u prime. So minus, what was u prime? So here I have it again. It's minus 4u, minus 4y prime, which is minus 4u prime e to the 2x plus cx e to the 2x minus 4u 2 plus c e to the 2x plus 2cx e to the 2x plus 4y, which is plus 4u e to the 2x plus cx e to the 2x. Great. Now let's see if we can simplify these things. Hopefully there is no computational mistake. That would be very unlikely, but let's hope. So so this is the only term which has the second derivative of u, so there is nothing I can do with this term. Let's look at the terms which they have u prime, right? So there would be this one and this one. So if I want to combine these two, so let's call one of them A, let's call one of them B. So what is A plus B? Let's combine these two terms. One of them is u prime times 4 e to the 4 plus 2c e to the 2x plus 2cx e to the 2x minus 4 times e to the 2x minus 4cx e to the 2x. Yes, that would be it. So let's see. This 4 e to the 2x cancels this 4 e to the 2x here, right? And then this 2cx e to the 2x cancels just two of these minus 4. So we would get minus 2cx e to the 2x. So the result would be equal to u prime, maybe I would write it in blue, would be u prime 2c e to the 2x minus 2cx e to the 2x, which I can write it as 2c u prime e to the 2x times 1 minus x. So that would be the combination of the parts which had u prime. Now let's look at the parts which have u. There is this part which has u. Let's call this one C. Let's call this one D. Should that be 4? I guess not, because we canceled and there was only 2 here. And then there is 2 here. So I'm assuming, yeah, I'm assuming it's 2. Maybe I'm making another mistake. You can tell me if I'm making a mistake, you can tell me where I'm. The coefficient of the second one. 4cx. You mean this thing here? It was 4? If that's what you're referring to, if you're talking about this one. But I cancel, it was -4, but there was also 2 here. And then 2 minus 4 became -2. You mean rather than -4, it should be +4? Yeah, I think you are right. Let me think. No, I think what I did is correct. You can unmute yourself and tell me. I think it is correct. I don't see any mistake.
I mean the 2cx e to the 2x in the first line.
Where here? Which line? This line?
No, the a plus b one.
Okay, so we have u prime. So we have. Tell me where up to which point you're agreeing with me. We have u prime times 4 plus 2c.
The 2cx e to x you have. It should be 4cx, I think.
Here are you referring to,
Yeah.
right? Yeah, that
Yeah.
is correct. That makes things easier. Thank you. Thank you very much. That's a great news. So very, very good. So they cancel each other. That's great. And so there's no this thing. Great. So it would be, what we are going to get at the end would be 2c e to the 2x u prime. Yeah, great. Well, now, what is c plus d? What is c plus d? Let's see. So we have 4u, I mean 4 as a number times u, and then we would have e to the 2x plus cx e to the 2x minus minus 2cx e to the 2x minus 2 plus c e to the 2x. Right. Now let's see what happens here. Well, this term would cancel this coefficient here, and e to the 2x cancels this one and makes it 1. It was -2, it becomes 1. And therefore, the final thing would be minus c e to the 2x times x plus c plus 1 times, there is also 4 times u. That would be the final thing. Now, what we want is, so you can see it's an example of a bad method for solving this this problem. The other method is a lot shorter, I guess. But let's follow this thing. Let's see where we are going to get to. So the sum of everything we had is equal to u prime e to the 2x plus cx e to the 2x. And then we had 2c e to the 2x u prime. And then finally, we had 4c e to the 2x times x plus c plus 1 times u. And what we want it to be equal to what? We want it to be equal to x squared, I guess. Yes, that is correct. We want it to become equal to x squared. Do we have any? Okay, let's see. Let's see how we can do that. That's yeah, well, great. That's an example of an equation. Well, that's an example of an equation which it's safe to say that not only that I have no idea how to solve, but well, I mean, I do have some ideas, but it's an example of a very complicated, well, let's say quite complicated equation. It's a second degree ODE, I mean, but it is quite complicated equation. So as you can see, I mean, I'm not even sure if it has a solution. I mean, there's a great chance that there isn't any solution. So as you can see, these methods don't necessarily work. So for this equation which we had, finding a solution with the other method was quite simple. So a bad method for solving this one. But we could do it with the other technique. Dx plus 4y. What was the other method? Well, the other method was finding a general solution, which we did, and then finding a particular solution, and then they add them. And here we have a second degree polynomial. So remember, the particular solution should also be a second degree equation. So something of this form. And we should just plug in this thing inside the equation. Now let's do that. So we have our equation. And because here on the right-hand side, we have a second degree equation, our particular solution would be also something second order. Now, if you plug that into the equation, it would be its second derivative. So the first derivative is 2ax plus b, and its second derivative is just 2a. So it would be 2a minus 4 times 2ax plus b plus 4y, which is 4ax squared plus 4bx plus c. And this thing is equal to 4ax squared plus, what is the coefficient of x? The coefficient of x is minus 8a plus 4b. That is multiplication, that's the coefficient of x. And the constant ones are 2a minus 4b plus c. And we want this to be equal to x squared, right? Therefore, the coefficient of x squared should be 1, because here the coefficient of x squared is 1. The coefficient of x should be 0. The constant one also should be 0, because on the right-hand side, the coefficient of x is 0. We don't have x. The constant one is also 0. So 4a should be equal to 1, which means a is equal to 1 over 4. And then minus 8a plus 4b should be 0. But since a is 1 over 4, minus 8a is minus 2 plus 4b should be equal to 0, which means b is equal to 1 over 2. And the last equation, 2a minus 4b plus c, would be equal to 1 over 2 minus 2 plus c should be equal to 0. Therefore, c is 2 minus 1 over 2, 3 over 2. So this particular solution is just 1 over 4x squared plus 1 over 2x plus 3 over 2. And the general solution is just the sum of this one with our homogeneous one. So maybe I would write it here. The general solution is c1 e to the 2x plus c2x e to the 2x plus 1 over 4x squared plus 1 over 2x plus 3 over 2 if there is no computational mistake. 3 over 8. Yes. Well, you can also check to make sure everything's correct. No, you can't say very complicated in the exam. So I was showing you that we have two different methods. Sometimes we had one example that one of our techniques work, the other one doesn't work. And this is an example which the variation of parameters, the one writing the solution as multiplication of two things doesn't work, but this other one works. I'm just letting you know that a lot of times we should find what is the best way to solve the problem. So I did not just let it stay like that. When I noticed that using that solution gets to a point which it's very complicated, I cannot continue solving it, I came up with another solution, right? The coefficient of C should be 4. Oh yeah, we multiplied everything by 4. You're definitely right. It is 4c, 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 4c. Then it would be 3 over 8. And then here we have 3 over 8.